What the heck is up, everyone? It's Jacob here, and in this video I'm going to be explaining the differences between a traditional internal combustion engine car versus a battery electric vehicle, and we're going to be looking at the differences of the systems on board of the car. So to start, let's start with a diagram of a traditional internal combustion engine car that we're used to. So this just kind of shows all the systems in here. So I'm going to go ahead and explain the main differences of the cars, the different components on board and how they operate. So without skipping over this, the most obvious thing, and this is really the only detail that a lot of people know about, between an internal combustion engine car like this and a battery electric vehicle or an electric car is the actual fuel system. They know that this takes gasoline and an electric car takes electricity. And while yes, that is the most obvious difference, but that's not the only difference. That is just the beginning. There's a lot of different systems in here that actually operate and function not nearly the same just because of switching that fuel source. So let's start with, of course, the fuel source. So in a traditional internal combustion engine powered car, we are powered by gasoline or diesel. It's normally a liquid fuel, oil-based fuel. So that's what we have here, and it's stored in a fuel tank. So that is our actual energy source to actually power this car, okay? And in a battery electric vehicle, we're using a battery, and that's this guy here. So this is the first difference, is the source of power. So this is very cheap, very inexpensive. It's just a fuel tank, and you have the fuel on board. This is very expensive and very technologically advanced. It's very hard to produce this versus a gas tank, a fuel tank. This is a lithium-ion battery. It weighs about 600 pounds in this case, and it stores less energy than a gallon of gasoline. So this stores about, this is a 24 kilowatt hour battery. This is from the Fiat 500e, and it stores 24 kilowatt hours of energy. So the energy content of this entire battery is less than 1 gallon of gasoline. So you might be wondering, how the hell do you run a car on that then? Because if your gas tank in your car was only 1 gallon, imagine having your gas tank be 1 gallon. You'd have to fill up every time you just drove a few miles. It'd be ridiculous, right? I mean, everywhere you go, you do have to fill up. So with this, the actual car itself utilizes the energy a lot more efficiently, so it doesn't run out as much as you would if you had only a 1 gallon gas tank. So that's the difference there. The main difference is the energy source. Okay, so now let's look at, if we're going to revolve a car to go around a specific energy source, such as gasoline or electricity, we need to figure out a way to propel the car with that energy source. In the case of a gasoline-powered car, we revert to the combustion engine, the internal combustion engine. So this is an assembly of a combustion engine right here, and we can see this is what's used to actually take the fuel, take the gasoline or diesel or whatever it may be. It takes the liquid fuel, combusts it, and uses that to generate a force to actually move the car. Okay, so if we're going to revolve our car around this engine, we have to look at what do we need to run this engine. And before we get into all that, let's look at, if we were to power a car with electricity, let's look at that assembly. So let me see, I have it right over here. So here is an electric car motor assembly. Now this is a motor, not an engine. A lot of people are going to have a hard time switching from the term engine to motor, but it is electric, so it's a motor. And so here is the actual part that powers the car. This is the motor, and this is the motor assembly. This is what you would find under the hood of the car. So I'm not going to get into all the details of this quite yet. We're just looking at the actual source of propulsion for the car. And in the case of the gasoline-powered car, we have the internal combustion engine, and in the case of the electric car, we have the electric motor. This is a three-phase electric motor. Okay? So now let's look at the needs of these motors, okay? Or of the engine versus the motor. So the engine has a lot of needs. If we're going to build a car that uses an engine, it has quite a bit of needs. So to start, you actually have to start this engine. And to start the engine, you actually have to have a motor to turn the engine, and you have to have an ignition system. So when you start up the engine, we're going to take in some gasoline, and it's going to start the engine. It's going to start spinning the engine with an electric motor, so it has to have an electric system on board, so it actually has to have a battery to start the car, because we have to initially start the engine before we get anywhere with this thing. So we have an ignition system, which is a set of spark plugs or heated coils in the case of a diesel vehicle, and we actually have to start the engine. So we have the ignition system of the car. That's how we start the internal combustion engine. So that's one system that we need. Then we need to actually cool this engine, because the internal combustion engine produces a lot of heat. In fact, it uses more of the energy of the gasoline. It uses more power to produce heat than it does to actually propel your car. Believe it or not, your car produces more heat than it does force to actually drive your car. So that's where, like I said, why you have so much energy in a gallon of gas. It's more energy than that entire battery in an electric car, because most of the energy is going towards heat anyways. And so we have to export that heat, if you will, from the engine. We have to take it away from the engine, or the engine will burn up. So we do that with the radiator. We have a water pump inside the engine, or next to it, however it's configured. We have a water pump that will pump water through the engine, and or coolant, if you will, but you can use water. In the case of cooling, we're going to use the term water because it's just easier to use. I'm just going to call it water. Of course, it is a coolant. It has to go a little bit above the boiling point of water, because water would boil over in an engine like this, and it would also freeze in the winter. But so we have a cooling system. It has to be able to dissipate a lot of heat, because this engine produces a ton of heat. Now, this, in the case of a gasoline car, is good because we can use this heat to actually heat the cabin of the car in the winter. So it's kind of a good thing, but for most cases it's actually bad. It leads to inefficiencies of the engine. It leads to just wasteful heat. So, but it is a plus when we want to heat the cabin of the car. Okay, so then what else do we need for the engine? We have to have an exhaust system. We have to be able to exhaust out the actual combusted gasoline, because when we put this fuel in, we combust it, it's going to come out as a gas, and that gas, whether it be, you know, CO2 and all the other crap that comes out with it, it actually has to go through the exhaust system. So we do, in these days in cars, it's actually pretty expensive, because we now have to conform to so many laws and crap as how to reduce the emissions. So we have the catalytic converter, which is a very expensive piece in the exhaust system, and things like that. So we have to have that for the gasoline engine. And what else do we need? We need to have a transmission, which I don't have pictured here, but we have to have a transmission because we have to be able to switch gear ratios, because when we run an engine, if we were to just hook it straight up to the drivetrain, it would stall as soon as we tried to step on the gas, because the engine simply just can't put out that much power. It can, but it would stall. So what we have to do is we have to put it through a transmission and put the engine up to high RPMs and gear that high RPMs down to low RPMs and more torque to actually get the car going. So we have to have a complex, very complex mechanism, the transmission. And so all that to keep this engine, to keep this source happy. This is what's going to propel our car. So there's quite a bit to it. Whereas, let's look at the electric system. What do we need to actually have an electric motor drive the car? So we explained all the systems that we need for a gasoline car. So let's look again at the electric system for an electric car. Let's see, where did it go? Here it is. So we have the motor itself. It's it's not very mechanical. There's not a lot of moving parts in it. There's one moving part, that is the actual rotor in the middle itself. That's the part that connects to the shaft and delivers the power to the drivetrain. Besides that, there are no moving parts in this. Okay, so it's a very simple design. All it is a motor. And what we have here is we have to give the motor power. It gets its power from the battery pack, just like the engine gets its fuel from the fuel tank. But we have to deliver it in an AC form here, because this is an AC motor, and we have to also be able to regulate how much power goes to this motor. We do that using this up here, which is the inverter module. And this is a very, very complex piece of technology. as far as if you were to compare it to any part in an internal combustion engine car, it's far more complex than anything you would see in there. It's like I said, no moving parts in here, all very just, it's all electrical, electronics, things like that. It's mainly just switching transistors and things like that to produce an AC wave that goes into this, a three-phase output that goes into this motor that has a varying voltage and frequency to match the speed of the car. Notice we don't have any transmission. We don't need a transmission. There's no need for it. This motor can deliver full torque at 0 RPMs, so we're not ever going to stall out a motor. This motor can produce as much torque as it needs to get the car moving initially, so there is no need to gear it up. Typically, it will go into a differential or some type of a gearbox with a single gear ratio. If I were to show you guys that, let's take a look at that real quick. This is the Fiat 500e drivetrain. We see here's the AC motor, and it goes into a single gear ratio gearbox, and it splits into the axles to go to the tires. So it's very simple, a lot simpler than having a transmission go to an engine. Less mechanical failures, and it's just overall a lot simpler. That said, it's very expensive. Again, this module here is very expensive. This motor is probably not as expensive as an engine, maybe similar prices, but probably a lot cheaper. But the entire assembly is probably more expensive than a gasoline engine at the current market price, because it's still brand new technology. There's not mass marketing, mass manufacturing of these engine assemblies, these motor assemblies. So then up here we have power distribution, high voltage power distribution, and things like that. Another thing I do want to mention is this also does need cooling. Now, it's not nearly as severe as the internal combustion engine. It has a light cooling. It has to export a little bit of heat, not too much, but to keep it practical and compact, instead of using convection cooling, it's not practical enough if you want to keep things small, lightweight, and compact. So they do have a little water loop here. Again, it's not water, it's that coolant crap. But in this case, it doesn't actually get hot. It doesn't even get hot enough to boil water. It just gets warm. We don't have to dissipate so much heat, and it's not even enough to heat the cabin of the car. So we'll explain heating here in a little bit when we go along in the other systems. So one big difference here, of course, when we compare this to the combustion engine assembly, is, like I said, once we've started up this engine is running in the car the entire time. This engine is always running as long as we have the car on, okay? Whereas this motor only is running when we're actually driving the car. This motor is not running any other accessory in the car. This motor is propelling the car, and that's it. That's all it's doing. So the main thing that's inefficient, the biggest inefficiency in a gasoline car, of course, is, like I said, the engine. It's so inefficient. It may be 25, 30%. I don't even know if we have engines today that are 30% efficient. So of all the energy you're putting into this car through the gasoline, only 25% of it is actually going towards driving the car. So you're going, damn, where's the other 75% going? It's going towards heat and just various other losses. Most of it is heat from the actual combustion of the fuel and friction and things like that. So you're going, well, why the hell, one question is, why don't we make it more efficient? Well, it's not very easy to make this kind of technology efficient. Of course, we're trying as hard as we can, but why are we using such an inefficient technology? Well, back to this diagram, it's a very plentiful fuel source. Gasoline is found. It's very easy to make. We have oil everywhere. It's a very easy and plentiful fuel source. We're not running out of it anytime soon. If we were starting to run out of gasoline, or it was becoming a fuel source that's hard to get or whatever, then even if we made it more efficient, it still wouldn't be really practical. But we have so much of it, and it's so easy to put into our car. It stores so much energy. 1 gallon of gas can hold, I think, somewhere like 35 megajoules or something like that. So it's a lot. I mean, a lot of power. 1 gallon of gas, we can afford, because it has so much energy and it's so cheap, we can afford to waste 75% of the energy towards heat and only use 25% of it to drive the car. Whereas in an electric car, we don't have the Where is it? We don't have the motor running all the time. This motor only runs when the car is running. When your car is sitting there at a red light, nothing really is running in your car besides maybe the radio or the headlights, but that's it. Whereas in a gas car, we have to keep this engine running even if we're not going anywhere. This engine has to still be running to keep all the systems running. It'd be impractical to shut off the engine every time you stopped at a red light. So you're wasting a lot of energy. But again, the gasoline has so much energy content to it. It's an affordable loss. You can easily waste energy with gasoline. Whereas with the electric, we don't have much energy in here. We only have 24 kilowatt hours of energy. And if we were wasting energy at the rate of this, we wouldn't even get off our damn driveway. But this is so efficient with how it uses energy that we get a lot further. So those are the main differences. We don't have an engine that's constantly running on this. We're only running the systems that we need to run when we need to run them directly from this battery. We're not converting it to mechanical power then to run the system. It's all being ran directly to this battery, directly from the battery. Whereas in the internal combustion engine, this is running the car, it's propelling the car, but it's also, we can see the serpentine belt here, and this is running everything else in the whole car. And it's important to know that this is where a lot of the systems differ. Okay, because in a car, we can't just have the air conditioning system running off gasoline. It just won't work. So we have the engine running off the gasoline, and the engine uses the mechanical force coming out of it to drive this serpentine belt to drive the air conditioning compressor, things like that. So let's get into the details. So as I was mentioning, let's see. Let me just make sure I didn't skip over anything. I have a little list here. So, yeah. So we have the serpentine belt here, and this is driven by the actual motor. And let's start with the 12-volt electrical system. So the 12-volt electrical system is needed in the car, again, to start the engine and run all the accessories in the car. So the actual car itself has a battery on board, just a 12-volt lead-acid battery that we're all used to. That's the car battery that starts your car, and it also keeps all the accessories running. But to keep that battery charged, it has to stay charged, and we do that with this alternator here. This alternator is driven by the serpentine belt, and it generates electricity to keep your battery charged all the time. Now, in the electric car, it's different. We don't have an alternator because we don't have an engine that's constantly spinning to keep the 12-volt system running. We're not wasting power like that. We're not just constantly keeping stuff running. So to keep the 12-volt system nice and happy, we do have 12 volts in an electric car still, because we have to have systems, the cabin systems, you know, heated seats, air conditioning, not air conditioning, but the air conditioning blowers, things like that, blinkers, lights, little things like that. Those all run on the 12-volt system, as does the car computer, things like that. So in internal combustion engine car, we're going to use an alternator. In an electric car, we're going to use a DC to DC converter. That looks like this. So what this does is this takes power from our battery. It'll take power from our high voltage lithium ion battery pack that I showed you in the beginning. So it's going to use that as the main power source, and it's going to output a 12-volt power just like the alternator would, a little over 12 volts, maybe like 13, 14 volts, and that's going to keep your 12-volt system charged. So instead of having it powered by the internal combustion engine mechanically through an alternator, we have it powered directly from our energy source, the battery pack, through this DC to DC converter, and we just step down the voltage, and that is what keeps our 12-volt systems running. Okay, so then now we're going to look at the air conditioning. So in an internal combustion engine, we just throw the air conditioning compressor, the AC compressor, right here on the serpentine. The serpentine spins the air compressor, and that is what keeps the R134A or whatever refrigerant that they're using in the air conditioning system. It's what keeps it flowing. So we do that with the serpentine in the combustion engine car, and in the electric car, we don't have the serpentine, so we have to use a direct electric-driven compressor. Everything is more direct electric-driven. That's the thing, is electricity can be used pretty much to power just about anything, whereas in here, we don't have an electric source to really power all this stuff, so we have to get it through the engine, because we can't just have a little AC compressor like this that runs on gas. How would we do that? Well, with a gasoline engine, and that's what we have here, a big gasoline engine. So in this case, for an electric car, the AC compressor to actually run the air conditioning system is just like this, same exact principle, it operates the same, but it's driven by a small little electric motor that's connected straight to the high voltage battery. So it's driven directly by the battery. We don't have this big huge conversion going here from gasoline to mechanical power, then to drive the air compressor. It's just battery to the air compressor. So that's the difference for the air conditioning. As far as heating, like I explained before, this engine naturally produces a lot of heat. So we can extract that heat through the heater core to heat the cabin. In an electric car, we don't really produce much heat. We don't waste a lot of heat, so we have to heat the cabin somehow. And this is done several different ways, but one common and easy way is through an electric heating element like this, a ceramic heating element. So this again is powered just by the high voltage battery here, and it's just a big heating element. And what we do is we just take power from the battery directly and it blow air through it, and it produces heat to heat the cabin. It's just a huge heating element, just like an electric heater you might have in your house. No different than that. These can be on the order of a few kilowatts, maybe like 4 to 6 kilowatts or so, like that, something like that. And then you have just a little bit of pulse width modulation on the input to vary that power to go a little bit lower if you want to. But the maximum power typically, you might see 4 to 6 kilowatts for the cabin heater. Now, a more efficient way, and something that I've been seeing a lot more recently, is what's called a heat pump. And it's literally using your air conditioning system backwards. Instead of producing cool air with your air conditioning system, we flip it and we suck heat out of the air. It sounds kind of ridiculous, but for those of you who know how air conditioning works, we actually suck heat away from the air outside, and we blow it into the cabin using an air conditioning system. So it's basically an air conditioning system backwards. If you've ever gone to your air conditioning unit outside in the summer, you'll know that it blows out a lot of heat, and that is the heat being extracted from your house. Same principle going on here. We use the heat from outside, and it extracts it from the outside and blows it into the cabin. It's kind of like an air conditioning system reversed, and that's called a heat pump. And now let's look at another example, that's power steering. Power steering, again, is just in an internal combustion engine thrown onto the serpentine belt. We have power steering right there. And what we do is it's just a big hydraulic compressor. Let's look at the ICE power steering. So this is the internal combustion engine power steering. So for power steering, we have our user input here. We give it a little bit of force, and it's going into this hydraulic. We have a hydraulic compressor here, and this is powered by the serpentine belt. We have our power steering fluid here, which is just kind of like an oil, if you will. It's what is compressed with this compressor, and it's what pushes these rods in and out to actually turn the car. And this is what drives, assists your power steering. It's power steering, and so when you put your input here, this hydraulic system really, I don't know how you would say it, enhances, if you will, I guess, the power that you're putting in. It just makes it a lot easier for you to turn. It amplifies the force that you put in to make the turning of these tires very easy. So again, in the electric car, we don't have that serpentine belt. It's not easy to just throw a hydraulic system in there. It's impractical. We could have a little motor driving this hydraulic system, but that's impractical. There's a lot more efficient way to do it. So let's look at the power steering system of the Ford Focus Electric. Let's see. So this is the Ford Focus Electric power steering. Again, same thing. You have a user input here, and it goes down into the power steering system, but it's driven by an electric motor, directly driven by the high voltage battery pack. Again, we don't have all those inefficient energy conversions through the actual internal combustion engine. We don't have the engine always running, so we have to pull our energy source from the battery pack. So that's where our power steering comes from. And then lastly, we have the braking system. Now, naturally, this engine has a vacuum. Now, a lot of people don't know this, but just like you have power steering, you also have brake assists. And when you push on your brake pedal, it's actually very easy for you to stop the car. Imagine, I mean, it's very hard to stop a car, going 60 miles an hour. Just pushing your foot on a brake pedal, it's pretty amazing that just a little bit of force can stop that whole car. And it's done using the vacuum assist on this engine. So like I said, this engine naturally has a vacuum on the intake manifold, and that is where it creates a vacuum that goes to your braking system. So when you push on the brake pedal, it uses this vacuum to assist your brakes. It basically is just like power steering. It uses a vacuum to help push your brake pads in and it helps the master cylinder push the master cylinder and helps you stop your car a lot easier than if you were to exert that entire force yourself. It uses this little vacuum pressure to help you brake the car easier. So again, the engine, the internal combustion engine, naturally creates that. In the electric car, we have to have an actual vacuum pump, and I have a picture of one. Right, where is it? All right, so here it is. So in the electric car, we have just, again, directly driven by the high voltage system, or I think it might even be driven by the 12-volt system. It's not much power it needs, but again, just a little motor driving the vacuum pump. So a lot of the systems are directly powered by the battery, as we can see. That's the main difference, is a lot of these little subsystems that we have to actually make the car run. Whereas in a internal combustion engine, we have this engine that's constantly running using the gasoline as the fuel source to power it. It powers all of the accessories through the serpentine. And in the electric car, all the accessories are powered directly by the energy source, the battery, through just individual little electric motors driving them all. And the actual main motor of the car that propels the car, let's see. The main motor of the car is only driving the car. That's all it's doing. It's not running all these other systems. Also, I almost forgot to mention that there is, in an electric car, regenerative braking, and this is actually the primary source of braking. Before it resorts to actually using disc brakes and brake pads, which actually stop the car using friction and turn all the energy into wasted heat, which is what is used on a traditional car. In an electric car, we use what's called regenerative braking. This is, like I said, the primary source of braking, but we also do have traditional disc brakes to stop the car if the battery is fully charged and it can't accept a charge, or if for some reason the regenerative braking system fails, or if it's cold out and the battery can't accept a charge. Anyways, what the regenerative braking system does is it actually uses this motor in reverse like a big alternator or a big generator. And what it does is it uses the actual momentum of the car spinning the actual rotor in here to generate power back into this inverter module, and this inverter module will turn that into a direct current and step it up to the battery voltage that is the battery pack voltage and charge the battery with that. So you're essentially taking the force of your car, the momentum of your car, and using that to generate power to recharge your battery. And that is how you stop the car. But that is not enough to actually completely stop the car. Once you get under about 10 miles an hour, again, we have to resort to the actual traditional disc braking, just because it becomes too much of a conversion to actually put that power back into the battery. So we actually have to resort back to disc braking. So that is the main source of braking in the car, is regenerative, mixed with the traditional disc brakes. Alright guys, and one last thing before I go and I end this, well, let's explain what are the main differences, because a lot of people look at electric cars negatively for some reason, and I think it's starting to change. We're starting to see a lot more hybrid cars on the road, and a lot of people, I think, just don't think they have enough power or whatever. And a really good example that broke this kind of image is Tesla with their sports cars, their electric sports cars, which can accelerate faster than most gasoline cars. So there's that image behind the electric car, and I think it will eventually start to transform. But there are some other drawbacks. So let's look at a drawback of this car. This car is all mechanical. There's a lot of moving parts in here. I mean, I'm not going to get into exactly how this engine works, but for those of you who know how an engine works, there's a lot of mechanical stuff going on here. You know, we have the pistons going on the camshaft, and they have valves in there. There's so many moving parts that it's eventually going to lead to a mechanical failure. At some point, something is going to wear out in here. We also have the lubrication system. I forgot to mention that in the needs of this motor. We have a lubrication system, so you have to keep it lubricated. A lot of things. We have to replace the serpentine every once in a while. The alternator is going to go out. Bearings, things like that. There's a lot of moving parts, and it's going to need a lot more servicing, okay? That said, let's look at the negatives of the electric car. So if we look at the electric system, there is no oil, there's no service. We don't really ever have to service the car. It's service free. There's not really many mechanical pieces in here. There's a couple bearings in this motor, and that's about it. So this motor is not really ever going to wear out like this would. With that said, this is power electronics in here. We have a power electronics module. And for those of you who know a little bit about power electronics, big transistors, things that are dealing with, tens of thousands of watts or more, even in this case, hundreds of kilowatts, hundreds of thousands of watts of power, you may eventually, most likely, encounter a failure in this module, in this power module, and it's going to be an expensive fix. It would probably cost on the order of a few $1,000s, but it would it's not as likely to fail, I would say, as an actual engine as far as mechanical failures on here, but it can happen, and it would cost about as much as it would cost to replace an engine. But I would say the chances of this are going to be that it's going to last longer than an engine. Okay, but let's look at the biggest drawback of an electric car, and this is today, and this is going to be, I think, one of the biggest drawbacks in the future as well, is the battery. The battery is massive. This is the best battery technology we have today, is a lithium-ion based battery that's actually being produced full force and used in electric cars. This is the best battery technology that we have, and it really simply, just put plain and simple, isn't good enough. We have limited range on these cars. So these, Teslas can go, a Tesla Model S can go on 300 miles on a really good day, a really, really good day, going with the wind blowing your car downhill. I mean, it'll go 300 miles, but more realistically, I would say a Tesla Model S can go somewhere around 250 miles, which is still really good for an electric car, and no one can afford the Tesla Model S. So an affordable electric car, such as this Fiat 500e, typically we're seeing ranges ranging from 50 to 100 miles of EV range, which isn't going to cut it for most people. It just isn't going to cut it. And we're seeing this increase, but one problem is even if we do have something like, say, a Tesla Model S at an affordable price, this battery is a very expensive battery, and this battery is going to lose capacity over time. It's sort of similar to if you had a gasoline car. Imagine your gas tank shrinking over time. Imagine if when you first buy your car, you have a 20-gallon fuel tank, and later on down the road, you have a 19-gallon fuel tank, that's 18, 17, 16, 15, and pretty soon, your fuel tank is only 10 gallons. It's only holding half of what it did before. That's what's happening with this battery. This battery, when you first get it, is a 24 kilowatt-hour battery. Over time, it's going to lose its ability to retain, it's going to lose its capacity. It's going to lose its ability to retain the energy in it. So it's not going to be a 24 kilowatt-hour battery over time. And after we put about 100,000 miles on this battery, it's going to have maybe 70% capacity. So it's only going to hold 70% of what it originally did, and it's just going to be downhill from there. So I would say after about 150,000 miles, this battery is going to become impractical to use in your car, and you're going to have to replace it. This battery pack here alone today probably retails for somewhere around $10,000 to $15,000. So it's a very expensive battery. This costs almost as much as an entire car, just the battery alone. So that is a major drawback of electric cars today, is the battery technology. Tesla is trying to solve this with their Gigafactory. They're trying to mass produce batteries at a lower cost, which they will, and it will make batteries cheaper, but it will not beat the fact that these batteries will degrade over time, and they will have to be replaced. That's only going to be solved by better battery technologies, which is going to come from, universities, chemists, things like that. Producing more of these isn't going to help the technology become any better. It'll help it become cheaper and more affordable, but it will not solve the fact that these batteries are going to degrade and going to have to be replaced. So they both have, you're going to be losing in either situation. I'm not trying to advocate here for electric cars and say they're just the maintenance-free, the best thing in the world. They are maintenance-free. There's very little maintenance, but when it comes to maintenance on an electric car, it is going to cost you big time, because it's going to cost more than a whole freaking car to replace this battery. In the future, like I said, I think these will get cheaper, but for now, it's a major problem. that is the main differences. I just wanted to kind of get those out and just kind of show you guys, because a lot of people are unfamiliar with electric cars. They don't really know how they work, and a lot of people, like I said, are just familiar with the difference in fuel source. They just, oh, this car runs on electric and this car runs on gas. But you got to understand that when we switch energy sources, when we switch from gas to electric, this whole serpentine belt goes away, and all these accessories that are traditionally just easily just little mechanical pieces are no longer just, they don't operate and function the same way. So that's pretty much it for this video, guys. I hope you guys enjoyed this quick little spiel about these systems and how they work differently in these different types of cars. And if you guys have any more questions, definitely throw them down in the comments below. And like always, have a good one.